Hello and welcome to yet another video on signals and systems. So we have studied in the past videos the Laplace transform, and we will just provide a brief introduction about the Z transform. You will be studying Z transform in detail in your digital signal processing, say 6th or 7th semester. But just for the sake of the completion, we will have a brief introduction about the Z transform. So it's actually the counterpart of Laplace transform. While Laplace transform is used for continuous time signals, Z transform is explicitly defined for discrete time signals. Again, it is a powerful tool, a powerful transform that helps in the analysis of the systems. So, generally speaking, the Z transform of a discrete time signal which we denote as x of n, it is defined as x of z is equal to summation n runs from minus infinity to plus infinity x of n into z raised power minus n, where z is a complex variable and it is typically given in the polar form r e raised power j omega. So which means x of z, yeah, r e raised power j omega is equivalent to summation n runs from minus infinity to infinity x of n r e raised power j omega n whole raised power minus n. If you kind of rearrange the terms, it will be minus infinity to plus infinity x of n, then we will separate r raised power minus n, and outside we will have e raised power minus j omega n. Let's call it 1. Now we know the discrete time Fourier transform. We have studied it in the third chapter, and it is defined as x e raised power j omega is equivalent to summation n runs from minus infinity to plus infinity x of n e raised power minus j omega n. So if you compare equation 1 and 2, yeah, in other words, if you compare the Z transform with the Fourier transform, you will see that the Z transform as given by this expression, it is actually the Fourier transform of this sequence. Just compare this and this. Right? So it is actually the Fourier transform of this sequence that consists of x of n multiplied by r raised power minus n. So we can say that from these two equations that x r e j omega, which is the Z transform, it is the Fourier transform. When I say Fourier transform, I mean discrete time Fourier transform of sequence x of n multiplied by a real exponential r raised power minus n. Okay? So mathematically we can say x r e j omega, it is actually discrete time Fourier transform of this sequence. Fine. So just like in Laplace transform where we had an additional sigma factor, यहाँ पे this is the additional factor, and it has the same effect that it improves the convergence property of your Fourier transform. Fine. Because this r raised power minus n, this is an exponential signal. It may be either a decaying exponential or a growing exponential, depending actually upon the value of r, depending whether r is greater than or less than unity. We have studied discrete exponential in our first chapter, so it can be either decaying or it can be either growing, right? Now we'll take a typical case for the fact that if for r is equivalent to 1, when r has a value of 1, which implies r raised power minus 1 is equal to 1 raised power minus 1, which will be back 1. Now for this typical case, r x of z will be x of e raised power j omega, which will be actually the discrete time Fourier transform of the sequence x of n. Okay, so x of z evaluated at z is equivalent to e raised power j omega. Generally z has a value r e raised power j omega, but if we put r equivalent to 1, we will be evaluating z transform at e raised power j omega, which turns out to be the discrete Fourier transform of the original sequence x of n. Now, if you remember in the continuous time case, the Laplace transform, is reduced to the Fourier transform when the real part of the transform variable is 0. If you remember, we had a variable s, which was sigma plus j omega. And when we evaluated Laplace transform at sigma is equivalent to 0, this was basically equivalent to the Fourier transform of the signal x of t. Okay. So similar kind of relation exists here, that if we evaluate z transform for z is equal to e raised power j omega, in other words for r is equivalent to 1, then z transform reduces to the what you call discrete time Fourier transform of that sequence. Now this is mathematically, but we know Laplace transform, and we have both algebraic in this expression for the transform, and we also have what is known as a region of convergence. Fine. So if we interpret in terms of region of convergence in Laplace transform, that is, so this property sigma is equal to 0, it actually means that the Laplace transform reduces to Fourier transform on the imaginary axis. Fine. In fact, वहाँ पे हमने prove भी किया था that Laplace transform, we can say that Fourier transform is a Laplace transform evaluated for s is equal to j omega, which from an R region of convergence point of view means that Fourier transform is Laplace transform evaluated over the imaginary axis, the j omega axis, which is the imaginary axis. Fine. Now similar kind of relation exists in the z transform. Fine. Because in z transform, the z transform actually it reduces to the Fourier transform when the magnitude of the transform variable z is unity, because what we have taken a special case r is equivalent to 1, which implies z is equivalent to e raised power j omega. And if you take the magnitude on both sides, because exponential ka magnitude is unity, you will get this thing. Okay? So we can say that z transform, just like your Laplace transform, it reduces to Fourier again this Fourier transform here means discrete transform. This is understood because we are dealing with discrete time signals. So the z transform reduces to Fourier transform when the magnitude of the transform variable, that is z, is unity. This is algebraically. Now if we want to express this thing in terms of region of convergence, just like we did in Laplace transform, So we can rephrase it in terms of the region of conversion, that Z transform reduces to Fourier transform. Again, this means discrete Fourier transform on the contour in the complex plane corresponding to a circle with radius 1. You must have done complex variables. So this basically, अगर आपके पास एक complex variable है r e raised power j omega in the complex plane, that is a plane wherein you plot the real and the imaginary axes. This represents a circle of radius r. Okay, so it will represent a circle, and this will be omega, and this will be circle of radius r. Okay. Now this typical case where r is equivalent to 1, we then say that Z transform reduces to Fourier transform on the contour in the complex Z plane corresponding to a circle with radius 1. So this actually means this thing, that you have the Z plane, real, imaginary, and on this Z plane I draw a circle whose radius is 1. So this point here is 1. Radius is from here to here. So this. Now if I evaluate Z transform on this contour, which basically represents the contour of the circle of radius 1, इसे हम कभी, we say it is a unit circle. It has a great significance in Z transform, as we will see shortly. Now if we evaluate Z transform on this, here Z is equivalent to e raised power j omega, we will be actually getting the discrete time Fourier transform. Okay, so just like in Laplace transform में आपका S plane था, you had sigma plotted against j omega, right? But here we use polar coordinates in Z transform. We have of the form r e j omega, so we represent this complex variable in the polar form like this in terms of a circle. Now for the typical case when r is equivalent to 1, it actually means Z transform reduces to Fourier transform, where the magnitude of the transform variable Z is unity, and in terms of region of convergence, Z transform reduces to Fourier transform on the contour in the complex Z plane corresponding to a circle with radius 1. In short, you have real and imaginary parts, and if you are evaluating Z transform along this contour, that basically is the circumference of the circle of radius 1, you are basically evaluating what you call the Fourier transform, right? Now with just like with Laplace transform, we can thus say that as far as convergence is concerned, because this is an important property that we are interested in, so for convergence of Z transform, we require that Fourier transform of x of n r raised power minus 1 should converge. Okay, because we have just shown here, if you look at this expression, let me just rewrite it here. The way we express our Z transform is summation n is equal to minus infinity to plus infinity x of n r minus n, then e raised power minus j omega n. Okay. Now for discrete time Fourier transform of this sequence to exist, we must ensure that it should converge, and this kind of becomes the condition for convergence. Yeah, finding the region of convergence in case of a Z transform. Okay. Now in general we will have values of R because this is the additional parameter where for some values your transform may converge and for some other values it may not converge. Fine. So generally, just like in Laplace transform, the Z transform of any sequence, it has associated with it a range of values of Z for which the transform converges. Okay? And this range of values, so let me put it here that in general, in Z transform, if we take for a sequence, it has associated with it a range of values of Z for which xz converges, and in this range of values it is referred to as the region of convergence, and this is an important part when Z transform is concerned. Fine. We had a similar definition for region of convergence in Laplace transform where we define region of convergence as the values of S for which x of S converge. So similar to that we have this. So let's take an example to understand in detail. Suppose we have a sequence x of n which is an exponential sequence multiplied by the unit step, right? And we want to discuss its Z transform. So from expression x of Z will be summation and runs from minus infinity to plus infinity, the sequence x of n multiplied by Z raised power minus n, which is turns out to be, for x of n we will write a n u of n into Z minus n. Now since u of n is there, so the summation will go from 0 to infinity because u of n is only has a value of 1 from 0 to infinity, so it will become like this, which we can further write like this: a z raised power minus 1 n. Now this is a geometric series, and this geometric series is equivalent to 1 divided by 1 minus a z minus 1 under the condition that this इसका magnitude should be less than 1, which means a should be less than 1 by z. Yeah, you can say z should be, magnitude wise, z should be greater than a. Right? Then we will have this kind of a summation. So x of z is equivalent to 1 divided by 1 minus a z minus 1, which will be 1 divided by 1 minus a by z. If you simplify it, it will be z divided by z minus a with the region of convergence that z should be greater than a. Fine. Now it is a rational, x of z is a rational function. We know the concept of zeros and poles, so we have 0 at z is equal to 0, and we have a pole at z is equivalent to a. So if I plot this, I will locate a point a. यहाँ पे I will have a pole, 0 will be here, and region of convergence is for z greater than magnitude of a. So it means this is my real axis, this is imaginary. If I draw a circle through this, the outside portion of this circle will be actually the region of convergence for this sequence. means outside this circle the value of this transform will be finite. Right? So quickly let's do another example, a similar kind. This time round we again have an exponential sequence, but it is minus a raised power n u of minus n minus 1. So we have a different kind of a unit step here, and you know that u of minus n minus 1 is actually equivalent to u of minus n plus 1, which means you will be first reflecting this unit step. So this is u of minus n. Then you will be shifting this sequence by 1 unit because plus 1 here towards left. So this will be the sequence. So this is a sequence which has a value of unity from minus infinity to minus 1. So if we try to find the z transform, it will be minus बाहर निकालते हैं, summation n is equal to minus infinity to minus 1, because in this range this is equal to 1, and internally we will have a n फिर z transform का z raised by minus n. So again you can just slightly rearrange the terms. We will change the order of limits from 1 to infinity, which means n will become minus n, z raised power minus n will become n. Then we can express it like minus n is equal to 1 to infinity a minus 1 z n. But again, to adjust the limits, we can start from 0 to infinity a minus 1 z n plus 1, right? Because for n is equivalent to 0, this whole quantity will be unity. Since I am including this quantity here, so we will have to add 1. Fine, yeah, we can express it as 1 minus summation n runs from 0 to infinity like this. Just to make this summation from 0 to infinity so that it becomes a standard sum, a standard series, so that we can solve this. Now this will be equal to again 1 divided by 1 minus a raised power minus z, given that this argument a inverse z is magnitude should be less than 1. So this turns out that x of z is equal to 1 divided by 1 minus 1 divided by 1 minus a inverse z. If you solve this, it will again come out to be z minus a, but here now we have to ensure that a inverse z is less than 1. Yeah, we can say z is less than a, right? So the thing is that if you compare these two expressions, we had, first of all, we had a sequence x of n which was a raised power n u of n. Then we had another sequence x of n which was minus a raised power n u of minus n minus 1. This also had a z transform of z minus a. This also had a transform like this. But इसका region of convergence was for z greater than a. That means it was outside the unit, outside the circle with radius a. And इसका region of convergence is z less than a. Fine. That is, it is within the circle of radius a. Fine. So let me just, so this was the region of convergence for the first case, outside this circle. In the second case, it is something like this, inside this circle. And if you remember, this was the same situation with the Laplace transform. वहाँ पे भी we had two sequences. Algebraically they had the same Laplace transform, but the difference lied in their region of convergence. So we are having a similar kind of situation here. So that means that Z transform, just like Laplace transform, it requires both the algebraic expression and the region of convergence. Right? So this was a brief introduction to the Z transform. So just like Laplace transform, it will also have an algebraic expression given by this equation. And then it will have some region of convergence, that is the value of Z, where this Z transform is finite. Fine. We'll stop this video. Next video we'll look at some properties of the region of convergence for the Z transform. Again, they will be quite similar to that of Laplace transform, and then we will try to express stability and causality in terms of the region of convergence for the Z transform.